Okay, let's see if I have time. Yeah, I have some time. 20 minutes to do this. Okay, factoring and the distributor property. Looks slightly familiar, but not entirely the same. Let's talk about some key concepts here. We are going to be using the distributive property to factor. We have used the distributive property to multiply a monomial with a polynomial, but we can also work backwards to express a polynomial as the product of a monomial factor and a polynomial factor. For example, if we have 1.6w squared plus 6w, this can get broken down into 6, or rather 1.6w times w plus 6 times w. And then we notice that it has a common factor, or a common term that they share together, which in this case is a w. And what we can do is instead add our 1.6w and our 6 together in one nice grouping here, while our common factor, our w, stays outside. And we notice that if we were to, let's say for example, distribute this w into here and into the terms inside our binomial, we will definitely get our answer, which we started from. So it's like we're moving backwards from using the distributive property. So we have to think a little bit more when solving these kind of problems. So for example, if we were to solve this problem here, we want to find what the greatest common factor, or the GCF, is for each of the terms. For example, 27. How can we break down 27 into each factor that it has? For example, if I were to have 9 times 3, because we're breaking down 27, right? 9 times 3 gives you 27. We can also break down our y squared into y times y. And we can also further break down 9 to look like 3 times 3 times 3 times y times y. Same thing for 18. We can break down 18 into, let's say for example, 9 times 2, but 9 can get broken down into 2 times 3 times 3, and then y is just alone. And from there, in order for us to figure out what the GCF is, we have to just look at what they have similar. For example, 3's they have similar, and also the y's here. That means our GCF is going to be 3 times y, or just 9y here. From there, if we want to use distributive property to factor out the GCF, we just have to think. Our GCF, greatest common factor, would be outside, 9y, while everything inside is going to be what remains, right? So for example, we have 3y here at the front, right? Because that's what we got from the 27y squared, right? 3 and y. And from there, the only thing that remains here on 18y is going to be 2, which we can also add here at the very end. So solving these problems, you just really need to find what the greatest common factor is for each of the terms, and then whatever remains that that's not included in the GCF, we would write out in a binomial, right? Same thing, another example here, a little bit of a bigger example. We can go ahead and break down for our first term here, which in this case is -4. Doesn't matter which one you make negative, but let's just make our first number negative. Let's say -2 times 2 makes -4. Same thing with -8. That's -2 times 2 times 2. A squared can be broken down into a times a, and b is just here in our first term. Our second term, we know that we have one singular a, so we'll go ahead and put that in, while b is squared, so we have two b's to work with. And finally, 2ab is just 2 times a times b. Now what, right? We just have to circle all of the terms that they share, right? To make sure that we only have one copy of each. The a's get shared throughout all of them, and one b gets shared out through all of them as well. This means our GCF for all three of these terms is going to be 2ab. And we can go ahead and break this down into what remains, right? So for example, 2ab will be outside because we're factoring it out. In our first term, -4a squared b, we have -2 and a still left over, so we'll write that in, -2a. Here in our second term, we have -2, +2, and b left over, so if we combine them, we get -4b. And last but not least, 2ab got factored out, and so if we factor things out, usually they're left with just a +1. as its remainder, I guess you could say. And this now becomes our factored version of our trinomial negative 4a squared times b minus 8ab squared plus 2ab. But we can also factor by grouping, right? Sometimes we have a trinomial or a four-term polynomial, and we can do something called factoring by grouping. But what is it, right? I think is the better question. Sometimes if we have, like I said, a four or more term polynomial, sometimes it might be nice to factor that out. It would always usually be something like a binomial times a binomial, and we'll go ahead and showcase that in the next couple of examples. For example here, what we want to do is separate each of, let's say for example, this four-term polynomial into two groups of binomials, right? Two binomials. For example, I want to probably keep, this should be a q, I think, q. I want to probably keep, and yeah, q should be there. I want to break up this four-term polynomial into two binomials. For example, I want to group up 3q plus 6 and also 4qr plus 8r together. And now I just think separately, what are my GCFs for each of these terms? In our first group here, I know I can probably take away 4r from this, and I just think, what should remain? Q should remain as well as is positive 2. Here on the right-hand side, if we take away 3, we can showcase that by saying plus and taking away 3 from this, so this looks like 3 times q plus 2. And we notice something. We have two similar binomials here, which we can technically factor out as well. That will look something like, let's say for example, we combine first our 4 plus 3 here, our 4r plus 3, and then our factored out q plus 2 from both ends, giving us a nice factored version of this four-term polynomial. So what are we doing here exactly? Let's just break down the steps one more time. We are grouping up two terms into its lonesome binomials, for example 3q plus 6 and 4qr plus 8r. From there we're thinking, what can we take away from them? What are their GCFs within those binomials? In this case, our first group shared 4r together, so we took that out, and we were just left with q plus 2. In our second group, we had 3 that was similar, the GCF for this binomial, and so we factored that out, giving us 3 times q plus 2, and we noticed that they shared similar terms that are being multiplied by q plus 2, so we can factor that as well, leaving us with just 4r plus 3 times q plus 2. Same thing here. But sometimes you might want to move some things around. For example, if you have a keen eye, we want maybe this term and this term to be grouped up together. You can definitely still move them around, just make sure that you keep the signs the same. For example, if I want to move this around so it looks a little bit nicer for me, I would probably move my negative 6u squared up one space to the left while keeping the 15. I mean, we can also maybe move that around actually. We can move the positive 5v first and then move the 15 down more. It's kind of like we're changing this into like standard form, right? So how do we factor this out? We still do the same thing. We're thinking and we're rather breaking up these two into separate binomials and thinking what their GCFs are for each of the groups. In our first group here, I think they definitely share 2, more than likely, and a u squared. And if we take that out, we're just left with v minus 3 here. Same thing here, looking at our second group here, we know that they share at least a 5. So if we factor out 5, we end up with v alone, and 15 divided by 5 gives you 3. Same thing. We notice, and we want to probably group up these two outside terms, our 2u squared plus our 5 here, alongside its common factor, which in this case is v minus 3. this would then give us our factored version of our 4-term polynomial, 2u squared v minus 15 minus 6u squared plus 5v. And just more grouping examples here. Honestly, none of this is really going to change. Sometimes we use fancy terms like additive inverses, which I'll show you a nice example of real quick. But really, it's just the same. We have to just kind of think about this a little bit differently. So how do we do this problem? I probably want to move some things around. For example, I definitely want to keep this the same, 2mk minus 12m, but I probably want to switch around these two terms, 42 and negative 7k. Switching them around, we get something like this. And let's go ahead and start factoring this, right? If we start factoring this, we notice that in our first group, we share at least 2m, and left over from this, we get k minus 6. Here on the second group, we notice that they probably just share a 7, but if we were to, let's say, for example, take away a positive 7 from this, we're left with a negative k plus 6. Which is not going to line up to what we have here. So what should we do, right? How do we make this better for us? If we notice that, let's say, for example, a 6 has to be negative, but it comes out to be a positive 6 here in the other group, what you can actually do is instead take away a negative 7 instead of a positive 7. But what happens, right? What happens to this? It's almost like we're dividing, each of these terms by negative 7. So if we take negative 7k and divide it with negative 7, this should give us a positive k, right? Because negatives cancel out. Same thing here. If you take 42 and you divide it with negative 7, you should get not a positive 6, but in this case a negative 6. So if we were to rewrite our second group, we would get k minus 6, because that's what happens when we divide by negative 7. Which now gives us two common factors, right? K minus 6. So grouping up our 2m and our negative 7, we get 2m minus 7, while the common factor that they shared was k minus 6. So it's basically like grouping like what we had here in our previous examples, but we're kind of thinking a little bit further, right? A little bit more in depth to, what we have going on for us, right? Sometimes we have to take away a negative number, unfortunately. Same thing here though. Going to be about like the same problem, I think, give or take. But I probably want to switch around these two terms in our first group. This gives me, let's say for example, negative 3ab to the 4th power plus 21b to the 4th power plus 4a minus 28. From here, we do the same thing. Think of what their greatest common factors are and factor them out. In our first group, we can probably take away, let's say for example, I want to probably just take away this negative 3. We could take away positive 3, but some of us might already see what might happen, so let's just go ahead and take away this negative 1, as well as the b to the 4th power. Doing so, we get a positive a here at the front term, right, the first term of our binomial. And here on the left, 21 divided by 3 gives you 7, and negative 7 to be exact. Same thing here, 4a minus 28. Their common factor would be 4. If we take away a positive 4, we get something like a minus 7. Now we just group up some terms together. We have negative 3b to the 4th power plus 4 times our common factor a minus 7 here. And that's kind of it. We can look a little bit further into part 2 of this, but as for our 2.5 section, I think this kind of